Okay, thanks everyone for joining our monthly UCNR water webinar. And some of may already know who am I, but just in case, I am Safiq Khan, Cooperative Extension Specialist in Water and Watershed Sciences with UC Irvine Natural Resources. And myself, along with my colleague Ellen Bruno and Faith Kearns at UC Water Institute, we organize these monthly webinar. We started last year, and this is our second year. And I'm really delighted today to host Dr. John Abatzoglou as our first speaker of this academic year. And John is an associate professor in the Department of Complex Systems. And his research really focuses on the climatology and trying to understand the science behind climate and how climate affects water, wildfire, forest, agriculture, and so on and so forth. And his lab not only focuses on trying to understand the underpinning and how these processes and drivers are connected, but also building a lot of the data and decision support tools that can help better manage our natural resources. So with that, John, take it away.
Great, thanks, Safiq. Let me go ahead and find the screen that I'm going to share. Where is it? Hold on 1 second. We did this a second ago and it worked fine. All right. Share my screen. There we go. Okay. Okay. Oops. Of course, I'm starting way at the end here. Yeah, let me go back to the very beginning. All right. So yeah, so thanks, Safiq, for that introduction. And thanks, everybody, for joining us on a Friday afternoon.
John, you're sharing your entire screen, your entire laptop screen.
I am sharing my entire screen. Okay, let me start this over again. Stop share. Let's do it again. Oh, here we go. All right, does that work much better?
Perfect.
All right, good. Okay, third time's a charm, right? Okay, so like Safiq said, I'm a climatologist. I work on trying to understand the climate system as well as its impacts on human and natural systems in the West. So it's not too much of a surprise that drought is one of the topics that I operate on quite a bit. And like Safiq said, my research climatology lab pores over lots and lots of data, right? Observations, models, paleoclimatic records. And honestly, most of the time, data is data. But to tell you the truth, increasingly, I have been using 4-letter words to describe recent observations. And cool is not one of those words. So with that, right, we're in the midst of another epic drought. And of course, we just went through one of these. So what's up? Yeah, and in fact, the 2012 to 2016 drought was perhaps the most extreme 2 to 3 year drought in the instrumental record. And then realistically, when we look at the paleoclimatic record, likely the most severe drought, sort of multi-year drought in at least the last 1,200 years. And of course, we saw a lot of direct and indirect impacts of that drought, including legacy effects that we are still sort of dealing with. And then flash forward to the last 2 years. We're seeing essentially the same sort of conditions play out in real time, right? Yeah, maybe a couple wet years between the 2014 to 2015-16 drought cured things, but maybe not so much, right? Maybe we're looking at this period, a longer term period of aridification. The drought that we're in right now, if we want to, we can call it as basically starting in water year 2020. And of course, what we've went through the last 2 water years is just an incredible combination of dry and then terribly hot years. And so we're seeing these scenes play out, right? These scenes of decimated reservoirs, wildfires, wells running dry for local communities, disproportionate economic impacts to the agricultural sector. Are we learning, right? Are we learning from these droughts? And perhaps we are, right? But in the midst of it all, it's hard to tell. So as a climatologist, what I want to do today is talk a little bit about, sort of give you the play-by-play. How did we actually get here, right? And I'm calling our current drought basically, again, starting from the water year 2020. we're going to also take a stab at trying to quantify just how bad conditions are. And again, I've used 4-letter words to describe what I'm seeing, so be prepared for that. We'll talk also about, some potential factors that were responsible for this, especially this water year. And specifically, we're looking for, what might we have been able to predict better? Or did we actually predict this? Right. And part of that will be, again, at the very end here, talking about the role of human-caused climate change in droughts like this that we've seen play out in California across much of the Western US. So again, going back to last water year, sort of the period from fall into more or less the end of winter here, October through March, much of the state had below normal precipitation. And these are a couple maps from the Westwide Drought Tracker. You can see an overabundance of sort of that orange hue there. So bottom 10th percentile of precipitation, a few locally record lows, including in Ventura County. And then temperatures were above normal for the long-term average, but realistically not terribly unusual given the last 20 years or so. So things look, definitely droughty by, say, April 1st, which is historically what we've looked at in terms of water supply outlook. And when we looked at sort of snowpack on April 1st, we were around 60% of normal. So that wasn't historically low, but it was low and would be considered a snow drought, similar sort of to what we saw last year. What really sort of, I think stands out in terms of at least this year in terms of drought is that the drought impacts or the manifestation of drought didn't end at the end of winter. And when we look at sort of what we were dealt from April through August, there's a lot of deep red, brick red on here. And that's indicating sort of the most extreme dryness on the left across basically sort of the central Sierra northward up into the Klamath Basin. And then temperature wise, essentially everything except the Central Valley and then sort of coastal regions had its warmest sort of April through August on record. So that combination in there, along with, pretty dry conditions during winter, really allowed for things to, get bad real quick, right? And so, very, very quickly, one of the means in which there are a lot of different drought indices that are out there. There's probably 6 million and growing. Probably one of the most frequently used drought index that's used across the US is the Palmer Drought Severity Index. It's basically trying to capture like a normalized soil moisture. And when we rank the Palmer Drought Severity Index over the past, 126-7 years or so, what we find is that at least for August, this is the worst it's been for a large section of basically from sort of, the mountains north of Ventura all the way up through the spine of the Sierra Nevada and then much of Northern California. So notably, this is worse than any year during that 2012 to 2015 drought for those areas. The difference is that I think it was 2014, that drought was centered a little bit more further in the San Joaquin region. You can look at the precipitation, and certainly there are some record dry conditions there, but of course, drought is more than precipitation. And so that's something that we'll get to here in a little bit. Just showing you a time series here, right? This is the Upper Sacramento. And you can clearly see just how much lower the August PDSI is relative to that historical records. So at least for single year events, some of the drought indices are suggesting this year is the worst it's been in the instrumental record, right? Of course, drought in California, 1 year drought, certainly has impacts. Throwing on top of that, of course, last year being pretty dry, you can kind of see where we've gotten to. So that's sort of a traditional way of viewing drought, right? Some sort of some sort of name ending in I, PDSI, etc. I wanted to show you a different way of visualizing drought that helps sort of, I think, separate out the contributions from precipitation on one hand, and then also the atmospheric demand. And in this case, we're looking at the potential or the reference evapotranspiration, right? So that's the water demand from the surface given a well-watered crop, right? This is how much moisture could be pulled from that land surface. I will note that the data for 2021 is not complete, right? We've still got some time to go, but this is sort of an estimate of where we might land. So this is a really, interesting plot. It shows us that a couple things, right? One is that water year 2020 and 2021 are pretty unique, right? They're way off here in the northwest quadrant. So they were not only dry, but they had incredible atmospheric demand, right? And that's sort of why we're seeing a little bit of a different character of drought from some other droughts. You can focus in on this cluster of brown, and this is sort of the 2012 to 2015 drought. It's sort of up there in that upper left-hand quadrant as well, but not as extreme as what we saw the last 2 years for the upper Sacramento. And then of course we can draw our attention to sort of the long-standing drought of record, or couple years drought of record in California, at least from a precipitation perspective, and that's the water years of 76 and 77. Pretty comparable precipitation wise, at least for this area, pretty big differences in terms of the atmospheric demand, right? And so comparing these 2 years here, effectively, we have on the order of 10% more atmospheric demand during the past 2 water years than during this historically previously dry year. The one last interesting thing here is, right, each individual year is plotted there, and you can see there is a tendency for years with very high evaporative demand to sort of follow dry winters, right? So that is something that we see not just in California, but actually across a reasonable portion of the Western United States. And the idea there is, as we dry out as the land surface is drier, it can actually heat up a lot faster. It's going to increase the vapor pressure deficit, and that's going to also increase the evaporative demand. So I wanted to just highlight a couple of, there's lots of impacts of this drought. Folks on the call probably know a lot more about the impacts than I do, but I want to highlight two, and this is a really nice tool from Mike Dettinger, and it's showing the dire state of Oroville Lake, which of course had to shut down hydropower in August because the reservoir levels got so low. And we're looking here at this year, at least at the lowest levels that Oroville has seen in the observational record. Did not refill at all really last winter, more or less flatlined. So that of course is of interest. 2 years back to back of very, very low precipitation along with high demand. And we can see the toll on our reservoir systems. And of course, fire's been obviously a huge thing the last 2 years. This is some data that I pulled in very recently. It's updated through September 8th. This year, if we look at just the forested area in California, it's the second highest in at least the last 5 decades, a bit behind last year, of course. And of course, what we have seen through the historical record, at least recently, is that in years where we have unusually high vapor pressure deficit evaporative demand during the sort of warm season, that enables fuels, that enables more landscape to burn. And so we see this relationship show up here at the scale of, this is all of California forested land. We see it show up also at the Western US scale. And at least currently, right, the story is the hotter and drier it is, the more fire area that occurs. Oops. So with that, what I want to do is talk a little bit about sort of, could we have actually anticipated this or not? And, also what might be responsible. Okay? And we're not gonna totally play the blame game, but let's just play along anyways. We did have a reasonably strong La Nina last year. And, if you look at the outlook right now, we're expected to have another La Nina. La Ninas often like to have sort of back-to-back years. So we're going to see that here this winter as well. And of course, for those of us who follow sort of, climate and teleconnection relationships in California, the story with La Nina is that it is reliably dry. When we had a La Nina year, it's reliably dry in Southern California, right? But not so much in Northern California. And realistically here, this is a nice product from the Western Regional Climate Center. It's showing us one of the measures of El Nino or La Nina. This is the Southern Oscillation Index on the x-axis. And then this is the October through March precipitation on the y-axis. And then this is, again, the Sacramento Basin. And, you know, there's maybe some relationship here, but, you know, I don't know if you want to run to the bank with an R-square of 0.03. Nonetheless, there is a really, really, really weak tendency for La Nina years to be a bit drier. Realistically, the sort of hinge point in terms of the dipole across the west for precipitation during an El Nino or La Nina for ENSO is right, you know, right around the Lake Tahoe region. So not totally reliable. You know, nonetheless, right, that's sort of where we fell this year. So, you know, we were off in that, in this case, the sort of the bottom right quadrant. Not a great relationship, but it is what it is. So what we can also look at sort of, you know, what did the atmospheric circulation look like last year compared to average? And here I'm just focusing on November through March. And on the left-hand side, this is the 250 millibar winds. It's sort of giving us an idea of the jet stream patterns, et cetera. And during a La Nina, we typically get the jet stream to shift to the north. The polar branch of the jet stream is stronger. The subtropical jet stream, not so much. And that tends to, you know, push precipitation more into the northwestern United States and less into the southwest. And if you look at 2021, we sort of saw that play out, right? You can see basically the jet stream is stronger on its northerly branch. Something, you know, if you look here, just off of the coast of California, especially sort of central Southern California, pretty weak flow. And this is, of course, an average over, you know, many days in the winter, but that's suggestive of really wimpy subtropical jet stream. And obviously the jet stream moving north was one of the reasons why we were very high, very dry, I would say. And that's sort of somewhat typical for La Nina, except I would say this has shifted northward probably a couple hundred miles from a typical La Nina pattern. One thing that, of course, you know, we sort of look for is can we predict years like this? And there are certainly tools, right? One tool is knowing the state of something like La Nina and other sort of, you know, teleconnection indices that have memory. Another tool is using climate forecast systems. These are essentially like weather forecasts, except they're sort of predicated on sort of longer lived components of the climate system, namely things like sea surface temperatures, you know, soil moisture, sea ice, etc. And I'm just showing you a couple of the forecasts from this system called the North American Multi-Model Ensemble. And this forecast on the left was one that was initiated or started in October of last year. And it basically is what it was saying, you know, below normal precipitation for much of California during December through February. And on the right-hand side, this is a forecast for February. And it also was basically suggesting drier than normal conditions for spring. So there might be something here in hindsight, looking at one sample suggesting that, you know, there was a suggestion that this was going to be a dry winter. The magnitude, though, not so much. It was, again, pretty incredibly dry, especially for the sort of the second half of, you know, the spring, et cetera. Okay, so atmospheric rivers, right? Did we have any atmospheric rivers last year? Very few and far between. So the atmospheric river did not run through it being California. It did run through the Northwest. And just to remind ourselves how important few precipitation events are for making up sort of California's water resources in an individual year. The one on the figure here on the left is from Mike Dettinger's work, basically suggesting that, you know, about 5 to 10 precipitation events per year contribute over half of the annual precipitation for parts of the state. And on the right-hand side, this is something similar looking at snowfall events. It's basically saying that your top 3 snowfall events are contributing, you know, up to about half of your total snowfall in the Sierra Nevada. So the bottom line is that realistically California's sort of winter season operates a bit like a home run hitter. We swing for the fences. Occasionally we do quite well, and sometimes we strike out. And last year we totally struck out, right? And so this is what this is a really nice figure from the Center for Western Weather and Water Extremes, showing sort of landfalling atmospheric rivers from last year. And there was like a magnet in the Northwest of sorts, right? All those atmospheric rivers basically made landfall in Oregon and Washington. Exceptionally few made landfall in California. There was this one here that made landfall in sort of the central coast and actually brought some pretty impressive precipitation and also low elevation snowfall records. But that was a single event, right? Really, really lack of atmospheric rivers. There is some literature that basically has looked at whether or not atmospheric rivers and El Nino are related. And it turns out that there's not much to suggest that there should be a change in atmospheric river landfalls, at least in Northern California during El Nino or La Nina. Okay. In addition to sort of the lack of the big events, we just didn't see much precipitation, period. Right. And so this is showing us just one station. It's showing us the station from Davis, California. And this is the number of days from October 1st up until whatever, it's more or less to present, where we had at least 1/10 of an inch of precipitation. And you can just see where 2021, water year 2021 is tied with water year 77 with 16 days of precipitation. So this is a sort of an umbrellas optional or windshield wiper optional year. And by the way, 16 days, that's the average number of days per year with 1/10 of an inch in Phoenix. So pretty dry. Okay, I want to spend a lot more time here talking about the role of climate change on droughts in general. And then I'll show you a little bit of some recent climate projections for the state of California, thinking about where we might be going in the next 30 years or so. And so, right, thinking about how climate change influences drought, there are a lot of ways in which climate change influences drought. There are a lot of ways to define drought, period. I'm just going to touch on two of them, right? One is, of course, a warming climate is going to influence the amount of precipitation falling as snow, and then also mountain snowpack storage efficiency. Basically, snow can melt out earlier in the year as well. So that's certainly going to change sort of the synchronicity of precipitation to available water in this very Mediterranean climate. It also might change the partitioning of precipitation in terms of how much goes to evapotranspiration versus how much goes to stream flow. The image on the right here is suggesting something about the sucking power of the atmosphere, right? And the idea here is that with climate change, we also expect to see acceleration in the vapor pressure deficit of the atmosphere, which is effectively the difference between the amount of moisture the air can hold, which is a function of temperature, and the amount of moisture in the air. And that, along with some other factors, ends up increasing the sort of the evaporative demand from the surface. So this is like effectively putting an additional straw into a drink, right? You're going to sort of suck that moisture out, whether that's soil moisture, whether that's vegetation moisture. Okay, so this is one of the figures, right, that when I look at, I use a 4-letter word to describe. This is showing here summer temperatures for the upper Sacramento, and summer temperatures across a lot of California were just off the charts this year. We had the warmest summer on record in a lot of spots and broke, I think this was 2017 was the previous record, broke 2017 handily, right? And we certainly have seen an upward trend in temperatures, and really since the year 2000, temperatures have fundamentally changed in California, in the Western United States, and a lot of other areas. What I also did here is I added, let's see, yeah, there we go. So I added on here, right, on the far right, this is sort of, when I look at the climate change projections from CMIP 6 for this region, I added on here, basically, this is sort of where the central estimate of temperatures from projections would be in these different years. And the bottom line here is that the temperatures that we saw, the summer temperatures that we saw here in California, at least in sort of the interior California, I would say, would be pretty typical for basically mid-century. And I should preface this by saying this is these scenarios I looked at were sort of moderate emission. I think they're SSP2, RCP45 for people who like acronyms. So they're sort of, moderate mitigation, not business as usual, if you will. Okay, so of course, snowpack is going to be important, right? We have seen depletion in mountain snowpack. We've seen all sorts of indicators. Those are really well documented, probably one of the most apparent sort of indicators that resonates with folks in the Western United States in terms of climate change. And the transition from rain to snow, the earlier melt out of snowpack certainly is going to modify a couple elements that relate to drought. You're going to change when runoff occurs. Runoff occurs earlier in the year. That leads to less runoff later in summer, leads to a number of the impacts, including sort of the compound effects of low flow and warm temperatures on fisheries. And then if we're thinking about sort of mountain ecosystems, right, the sort of ablation or lack of snowpack to begin with, that is pretty important. That ends up actually removing a key component for water resources given the Mediterranean climate that we have. And so that reduces plant water available, reduces soil moisture, really profound in mountainous regions. This is a quick figure here from a paper that some folks at the Department of Water Resources worked on and I helped out with, and we were just looking at some of the changes in the freezing level, right? The 0 degrees Celsius elevation, if you will, during the winter season here over whatever, this is 70 years, over 70 years, right? And the story here is we've seen more rain and less snow. And the percent of precipitation falling as snow is of course declined, and it's declined the most in the spring, which is consistent with springtime. Your freezing level goes up and you start to get closer to where you might transition from rain to snow. And another thing just trying to highlight some of the work that I've been involved in here. Another thing, right, given that we have had back-to-back snow drought years, right? Snow drought years basically is referring to the fact that your maximum daily snow water equivalent is in the bottom quartile historically, right? So back-to-back snow drought years in 2020 and 2021. Historically, this happens around 6 to 7% of the time. Right. We sort of expect, and at least with some of the projections that have been done, that these sorts of back-to-back snow drought years will become much more favorable. Not too much of a surprise given the warming, but you can see that they're most favorable, of course, at sort of your mid-elevation mountains. You can see the high Sierra there. There's less of a change because those areas are less sensitive to warming in terms of the precipitation seasonality. So I'm going to spend a little bit more time here talking about the evaporative demand, right? The sort of the sucking power of the atmosphere, if you will. And I think I hit on that first point, so I won't go through that again. But evaporative demand is a function of atmospheric conditions, also a function of vegetation. I'm going to not deal with that right now because I'm going to look at just the standard grass Penman Monteith evapotranspiration, which is a function of basically temperature, humidity, solar radiation, wind speeds, etc. And you sort of get the idea here that as you have higher temperatures and higher vapor pressure deficit, that is going to increase the pull of water from the surface to the atmosphere. You'll get something similar if you have strong winds as well. Okay. So I'm going to highlight here 2 studies that have actually looked at this effect, right? What is the effect of increasing temperature as realized through increasing atmospheric demand on drought? So this is some work that Park Williams led, looking at the 2012 to 2015 drought in California, and the idea here is that most droughts, right, sort of the leading driver of most droughts that we think of is a lack of precipitation. And that tends to be the case here. And you can look at sort of the contribution from sort of precipitation or the supply side versus demand, right? And it turns out that precipitation is the leading driver here. The more interesting thing here is that we looked at the observational record, and then we ran these counterfactual models, and the counterfactual models basically said, well, let's look at how drought as realized through the Palmer Drought Severity Index would have played out if we didn't have this long-term trend in temperature. And the story here, you can compare the two maps on the left. The story is that 2012 to 2014 period would have been bad, but not nearly as bad. And I think the conclusion here is that, effectively the warming trend attributed to human-caused climate change made that drought period about 8 to 27% more extreme. Okay. So that's sort of a short-term drought. And you may have heard that we're in a longer-term drought. And again, that the definition of mega drought is probably as contested as the definition of drought, given the variety of ways to do that. But looking at the greater southwestern United States, which is this little inset up here on the upper right-hand corner, we can basically say that the long-term drought, say 20 years or so, that we've experienced basically since the turn of the millennia, it rivals the worst drought in 1,200 years for the broader Southwest. So that doesn't necessarily apply to any given spot in California, but the broader Southwest, it's been incredibly dry, right? So these protracted droughts are certainly interesting. They have different impacts than, short-term 1-year drought or 2-year droughts, right? They represent sort of a longer-term aridification. Obviously, there may be corrections to that, right, as we enter into wetter periods, et cetera. This is, again, some work that Park Williams led, and we did something very similar where we looked at the observational record tagging along here, right? Prior to the observational record, we bring in the paleoclimatic record, and we ran counterfactual simulations as well. And what we found there is that the role of human-caused climate change was actually much more substantial, namely that about half of the magnitude of this sort of protracted drought across the Southwest could be attributed to human-caused climate change. Okay, and we have been getting questions about, is this drought going to recover? Are we gonna see a recovery in this drought? When we released that paper, we had data up through, I think, 2018. And 2019 was a reasonable year, pretty good year. And then we had 2020 and 2021, which were, terribly dry, not just in California, but much of the Western United States. And so some crude estimates of where we stand today. The red, this is showing trajectories of drought, starting from the sort of commencement of drought, if you will. The estimates for 2021 is that we're down here, which basically makes it the worst sort of 22-year drought in the period of record. There's some uncertainty, obviously. The blue line here is showing us, this is the trajectory of drought in terms of soil moisture, summer soil moisture that would have transpired in the absence of human-caused climate change. And the story is that climate change has taken a pretty bad long-term drought and made it effectively the worst in 1,200 years. Okay, so that's pretty substantial. The IPCC's Working Group 1 report has come out recently. It's 3,000 pages. I'm assuming everyone's read that all. Just highlighting here, one of the synthesis figures they have for attribution of human-caused climate change to what they call agricultural and ecological drought, which, more or less is going to be related to soil moisture. So very similar to the things that we were looking at recently. And the idea here and if it's not clear to you, this is a map of the world. It's abstract art, apparently. But this hexagon right here represents Western North America, which is where we are. And the story here is that there's medium confidence that humans have already increased the occurrence of agricultural and ecological drought. Okay, and you can see that playing out in other areas of the globe, including other Mediterranean climates, if you look closely here. Okay, so I want to conclude here with some of the near-term trajectories that we could see here in the state of California. And I'll preface this by saying this is really preliminary. This is me playing around with some data and wanting to share with folks. So with help from some collaborators, I've got about 132 simulations of CMIP6. This is the sort of most recent generation of climate models. And I'm going to show you here results, just raw model results, right? Not downscaling or doing anything fancy. Some raw model results summarized for the state of California for a few variables. So, temperature wise, right? And again, so red is showing us the observed data, annual values, and then I'm showing you sort of the spread of different models. And the story here with temperature, not surprisingly, we followed the trajectory of temperature reasonably well. We again expect to see continued warming, similar to the plot I showed you earlier. What is today a record hot year will be pretty close to sort of average by sort of 2050 or so. These scenarios here, right? I'm not looking at different emission scenarios. This is just sort of the, moderate emissions pathway. The reality is that at least for near-term projections, the emission scenarios don't matter a ton. They do matter a lot post 2050. Okay. So at least for the next 30 years, we expect warmer conditions. Not a surprise, not much of a surprise, and realistically not terribly different from previous generations of climate models. But nonetheless, we're following that trajectory quite well. One thing that is sort of interesting, and I don't know if it's been emphasized too much, is the seasonality of warming, right? So when we look at warming and I say, it's going to be warmer by 1.5 degrees Celsius, there's actually an interesting and distinct signature to the warming, in that we end up, at least the models tend to project more warming in the warm season. So if you like hot summers, I have something in store for you here. And that is, that has potential impacts rather than just assuming it's going to be a fixed warming rate over all seasons, and same for Tmax and high temperatures and low temperatures, if you will. So this is something that we do see across the Western United States as a whole as well. Part of it is associated with enhanced land surface drying, begetting increases in temperature during the warm season. This one is showing us, right, that measure of atmospheric demand. So here, what I've done is just calculate the reference, Penman-Monteith reference evapotranspiration for grass. And we've also incorporated a factor that accounts for elevated CO2. And the idea here is that as CO2 increases, plants close their stomata, and that can potentially offset some of the increases in evaporative demand. They're less able to give up water, essentially, as we have elevated CO2. It turns out, though, that the effect of the CO2 effect is, it buffers the change, but the change is fairly substantial, right? In that we expect to, sort of the projections are on the order of 25 to 100 millimeters more evapotranspiration annually than we saw in sort of that 81 to 2010 period. Okay, so that obviously is going to prime us for certain types of droughts. It also may translate, depending on agricultural practices, may translate into increased water demands for obviously our state's agricultural sector. The big one, of course, is precipitation. Are we getting any better with precipitation? Are we resolving uncertainty? Can we say for sure that it's going to be wetter or drier? The story here is that we have good agreement amongst models. The agreement is that they disagree. So we, like previous generations of climate model scenarios, California is not expected to see a ton of change in precipitation. Some models say more, some models say less. On the whole, though, not much change, right? If you look at some of the extreme members, there's a slight increase in wet extremes. The dry extremes, a little bit difficult to say, and the gray line here is supposed to represent sort of a 1 in 20 year event, and so the wet extremes increase just a little bit. We do see one thing that we do see that may be relevant in terms of thinking about drought and thinking about the Mediterranean climate and mismatch between water supply and water demand, is that the models do suggest a seasonal compression in precipitation. So that namely means slightly less precipitation in the shoulder seasons of fall and spring, and more in winter. So that, of course, that's of course interesting by shifting more precipitation to midwinter. If you're thinking about snowpack, there may be some slight compensation there because it's more precipitations falling during the coldest time of the year. But then, of course, if we're worrying about sort of water resources for, natural vegetation, et cetera, less spring precipitation, less fall precipitation, not great, because that's what we've seen in recent years, and it hasn't worked out so well. And I'll end with this one figure. This is a new study that Ben Cook and others put out, and they looked at the Southwest region, and so the results may be a little bit different for California, but I don't know how different. I think the general theme works quite well. Effectively, what they show here is that the risk of an extreme drought, right, a single year extreme drought, so maybe that's like a year like 2021, right, the lowest PDSI on record. In this case, they looked at soil moisture, but it'll be fairly similar. The idea here is that at least by the end of the 21st century, there's projected to be an increase in the risk, the annual occurrence, how frequently these events may play out. At least for single year droughts, there's also a substantial benefit by having emission pathways in worlds where we basically we're curtailing carbon emissions. So nonetheless, though, there's an increase. The more sort of important point, perhaps, when we're thinking about longer term droughts, and this is consistent with those two studies I showed you earlier, is that we expect to see these longer term droughts much more frequently in the future, right? So this is here looking at, I guess, a 21-year drought, similar to the Southwest drought that we're in right now. And even this figure doesn't suggest there's a substantial benefit in the sort of SSP126, which, again, acronym central. This is, a pretty aggressive climate mitigation pathway. Nonetheless, though, we expect to see increases. The magnitude, though, is much more extreme when we look over here on the right-hand side, and that is that red color there. That's more of a business as usual pathway, continuing to rely quite a bit on sort of, carbon-intensive fuels where economically feasible. So with that, I'll conclude with just a few thoughts. We've had a lot of very, very dry years in California. It's been a staple of California's climate in the past. And of course, California is a state that is renowned for having a pretty volatile hydroclimate. We're used to rapid, extreme swings, but the swings that we've seen recently have been something else. Using a couple of the measures, right, we can say, at least preliminarily, that at parts of Northern California, the most extreme in the instrumental record. Droughts, right, are these sorts of droughts like we're talking about are usually due to a shortfall in precipitation. Check that box. We lacked atmospheric rivers. Check that box. But what we're also seeing, right, not only from the recent 2012 to 2014, 16, whatever drought and also this recent drought, is we're seeing these really hot droughts. So we're seeing these compound hot, dry extremes that's increasing the evaporative demand. And it's tipping the scales towards years like what we're seeing this year and towards 20-year periods like sort of we've seen the last 20 years. We will have some wet years along the way. So with that, I will stop and see if there are questions. I know there are some in the chat box. And I think you're free to type in questions in the chat box or raise your hand, I guess.
Yeah, thanks, John. Yeah, that was fabulous. Nice overview. Yeah, I can see there's a question in the chat. It says, is there a typical La Nina pattern?
Yeah. Oh, and is there atypical or atypical?
Yeah.
Is that there's a normal La Nina pattern, and the normal La Nina pattern would be basically the polar branch of the jet stream is substantially stronger. Southern California and the Southwest and the Southeast are dry, and the northern tier of the country is wet. And we sort of had something similar to that this year, except let's say the whole pattern has shifted north, basically putting Northern California into the dry sector. It's sort of usually on the shoulders of being dry. It's in the middle of the seesaw, if you will.
Any more questions? I got a couple, but I will hold on.
Safiq,
Yes.
Safiq, this is David Lewis, and John, thank you for a really great presentation. And I appreciate that today was about drought, but I wonder if you'd help us a little bit about the implications for you just talked about it as you wrapped up, the truncation of the delivery of precipitation and its implications for also more severe flooding. And just,
Right.
I'm thinking about resilience and keeping our memories and adaptation for both extremes, if you will.
True, right, yeah. So, right, that truncation is really interesting, right? Because, and the fact that we're seeing the models project more precipitation in midwinter, I don't think that there's not any, the projections are not for more frequent precipitation. So that would suggest, and I think there's other studies that suggest, more extreme precipitation events, right? Atmospheric rivers included. We sort of generically expect precipitation extremes to increase by 7% per degree Celsius warming locally. So that certainly would set us up for, mixing in some very wet years, along with, sort of a tendency to have dry summers as well. I think that is certainly something to think about for the flooding angle, because long term, we're certainly shifting the odds towards extremely dry summers, but there will be some very wet years in the mix as well. And that's, probably why on the balance, we generally don't see much of an overall change in annual precipitation. I don't know if I totally answered your question, but.
Okay, yeah, next question is, thanks for the amazing presentation. How can we improve sub-seasonal to seasonal forecasts for California? What are some dimensions that have scope for improvement?
Yeah, good. Yeah, that's a good question, Vivek. So there's certainly sort of seasonal and sub-seasonal forecasts that are sort of dynamical. They're run similar to like weather forecast models that some of the large agencies are producing. And so I think I showed you a seasonal forecast, right? There's also sub-seasonal forecasts. Those are sort of looking at what the forecast might be beyond sort of the timescales of weather. So like, what might be happening, 2 weeks, 3 weeks, 4 weeks from now. And that can be really important if you sort of highlight an increased chance for, exceptionally wet conditions. I think the general status of sort of sub-seasonal and seasonal forecasts in California and the Western United States is they're not great. And so there may be prospects to improve them, possibly using, some of the observational indices that we see. So that is an active area of research that I know a number of people are working on. Maybe they have improved. I don't know. I don't hold out too much hope for precipitation forecasts beyond 2 weeks, but that may just be because I think it's always going to be dry.
Yeah, more questions for John.
Yeah, hello. I have one question. I really interested in the 1200 years, like the reconstruction soil moisture. Can you move to the slide? And is this data reconstruct from the trailing data or the sediment or something else?
Right, good question. So these are constructed from paleoclimatic tree ring records.
It's the training record. So do you have the more information about like the data for the like the 800 year or 900 year something, like if they?
Yeah, there's absolutely, I believe these data are available. And you can send me an email later and I can either direct you to the lead author or help you figure out where that is. I think this is part of sort of drought atlas reconstruction, where they've identified trees that are really good at sort of sensing elements of precipitation or sensing elements of summer soil moisture. Blue oaks are great. Like I've done a little bit of work with blue oaks, and they are fantastic rain gauges. Probably among the best, maybe better than my own ability to record precipitation.
Yeah, sometimes I look at the paper and the records for the 800, 900, maybe it's just 1 or 2 records. This made less confident.
Right.
Yeah, thank you.
You're welcome.
Okay, maybe Stephen, you go first, and then Ryan.
Hi, John. Wonderful presentation. I'm an economist, and so a lot of this is a bit foreign to me, but I've been starting to work in the last year on a project about the impacts of drought in Brazil on agricultural productivity and poverty. And so that's forced us to do a lot of reading about drought and how it's measured. And I'm wondering if you could comment on, you used the Palmer Drought Index, and how important is it to look at different dimensions of drought, like frequency and duration and severity and geographic extension and those kinds of things?
Yeah.
I'll stop there. Thank you.
Yeah, you're touching on one of the challenging topics of how do you define drought in general. PDSI is not the best measure, especially in the Western United States. It doesn't treat snow appropriately. It treats all precipitation as rain, more or less. So it's not the greatest. There are more sophisticated approaches. I do think that things like the longevity and the severity of drought may be important. And it's sort of also from the impact side, sort of the timing of drought relative to important sectors, right? Whether that's agriculture, whether that's the ability to generate runoff. There are so many ways to slice and dice out, you know what I mean, drought that my research group has developed something called the Water Watcher tool that allows you to go in and basically look at all the different flavors for drought and decide which flavor you like the best, because there are too many. But I think you're right. That's sort of tying the impact with the index can give you some pretty different results.
Thank you.
John, I had a question. I know you do a lot of the winds in California. I was just curious if there's much correlation between these drought events and how wind severity for Santa Ana's, Diablos, the different wind events we have.
Yeah. No, I don't think we've looked at that. That would be a really bad thing if they were correlated to one another. But that's a good question. I don't think folks have looked at whether or not drought modifies the potential for things like Santa Ana wind events. We're all sort of wondering how the Santa Ana, Diablo, et cetera season is going to shape up. And my general knowledge is that we don't really know. We're just hoping the precipitation comes first.
Yeah,
that's something to look at, though. It should be simple enough. So if you want to look at that with me, send me an email. You can take a look.
Sounds good.
I have one more question in the chat. Says this is supremely depressing for biodiversity in the Sierra and elsewhere, particularly for organisms adapted to weather drought, but not multi-year extreme drought. And with the warming spring, precipitation hitting critical breeding periods for many organisms, what would your message be for resource managers in the Sierra? Any
signs for hope?
Any signs of hope? Yeah.
Yeah, I think the hope may be that certain species are able to, some species may be able to shift their phenology a bit, and some species we are still going to see, some years that will be cool and wet, and maybe have snowpack sticking around. So I think the species that have multi-year lifespans might be a little bit more opportunistic, may be able to deal with that. There may also be, what do I want to say, microclimate or niches where snowpack on north-facing slopes may hold on longer, and those may be refugia, if you will, at least on the snow side. But yes, I do think I agree with this being fairly depressing. I don't think every year is going to be like what we've seen the last 2 years. I don't know what this year is going to hold, though.
Yeah, the next question, I like it. It says, it seems we should be talking more about adaptation to a more arid climate in California. When do we start calling this acidification rather than drought? It might change mindsets from treating drought as a periodic disaster or adapting our systems to a more arid future.
That's right. Yeah. So yeah, all these drought metrics are relative to some base period. Usually that base period is in the past sometime. And we've certainly shifted. If you look at some of these drought indices, there's been a shift towards a drier conditions. We certainly have had wet years punctuated between these dry years, and maybe there's some tendency for us to sort of forget all the things that we applied during drought conditions. I think there is some thought in terms of, looking at trying to treat these drought indices as a moving target, similar to how we treat sort of climate normals. So rather than comparing how hot this year is relative to 100 years ago, look at it relative to the past several years and just admit it's warming and there's acidification going on. And that may help us with some adaptation methods. Yeah.
Okay, so the last question I have, John, you were talking about the blame game, and I'm just curious how much we can blame to the mismanagement when it comes to intensification of drought. Mismanagement in terms of, our land, forest, vegetation.
From these climate measures, none, right? But if we're thinking about things like stream flow or runoff, water availability, then I think there is a way of actually trying to attribute and play these sort of counterfactual scenarios out. How would stream flow look like if tree density was substantially less in the Sierra Nevada? How much moisture is being taken out because we've had a legacy of fire suppression? And we may be seeing that play out soon, though. Not an experiment, but because so all those sorts of things are going to be really interesting because of the changes that we've seen here in terms of fire in a lot of our forested areas recently. That's a good question to actually tackle this. Yeah.
Good. Thanks, John. I think with that, we're right on time. So please join me in thanking John for taking the time and providing this nice overview of what is currently happening around California's water. And our next speaker of the series will be Maura Allaire from UC Irvine, and she will be talking about water economics. So do join us on October 15th. Again, Friday, 3 p.m. Pacific. And have a wonderful rest of your Friday.